The gamma function is a function that allows us to extend the idea of factorials to numbers that are not integers. Now, we all know, for example, that 5 factorial just means 5 times 4 times 3 times 2 times 1, which is 120. But what about 5.3 factorial or 1/2 factorial? Can we make any kind of sense out of these? Well, the gamma function allows us to make sense of these. And in fact, according to gamma, 5.3 factorial is about 201.813. And it's a decimal that goes on and on. Notice it's bigger than 5 factorial, but it's not as big as 6 factorial, which is 720. Now, it turns out that 1/2 factorial is the square root of pi over 2. So this is all pretty interesting, but where are these numbers coming from, and why is pi getting involved with factorials? So here's how we define gamma of n. For any positive number n, gamma of n is defined to be the integral from 0 to infinity of x to the n minus 1 times e to the minus x dx. So for example, gamma of 4 is the integral from 0 to infinity of x cubed times e to the minus x dx. Now, it's going to turn out that gamma of 4 is actually 3 factorial, so it'd be 6 is the value of this integral. In fact, for any positive integer n, gamma of n is going to be n minus 1 factorial. That's what it's going to turn out to be. But I should also point out here that we're not restricting n to be integers. N can be any positive real number. In fact, very often people use the letter x in the definition here instead of n. And when they do that, they change these x's to a different variable, such as t. But I prefer to keep it this way, using n's and x's, as long as we remember that n does not have to be an integer. Now, what does all this mean graphically? And we'll start by looking at gamma of 4, this integral. So I've graphed the function f of x equals x to the n minus 1 times e to the minus x, and I've made a slider for n, and I've set the slider to 4. So this function here that's graphed is really x cubed times e to the minus x. Now the area underneath this curve, right, the integral from 0 to infinity, so which represents the area under the curve from 0 to infinity, this area is gamma of 4. And it's going to turn out that that area is actually 6. It's 3 factorial. But notice we can move this slider. And so, for example, if we look at gamma of 5, so our function now is x to the 4th times e to the minus x. Gamma of 5 is the area underneath this function between 0 and infinity. And it turns out that this area is 4 factorial. It's 24 square units. But notice that n does not have to be an integer. So we could ask, what's gamma of 4.7? And that's going to be the area underneath this curve. And that's what we're going to sort of think of as 3.7 factorial. Now let's go ahead and do some computations. So we're first of all going to figure out gamma of 1. So we have our definition of gamma of n right here, and we're going to plug in 1 for n. And so up here we have 1 minus 1, which is 0. So gamma of 1 is the integral from 0 to infinity of x to the 0 times e to the negative x dx. But x to the 0, of course, is just 1. So we have the integral from 0 to infinity of e to the negative x dx. And this is not a hard integral to do. The integral of e to the negative x is negative e to the negative x, which is just this. And when we evaluate from 0 to infinity, we end up just getting 1. So gamma of 1 is 1. Now, we could ask, what is gamma of 2, gamma of 3, and so forth, and try to figure out those directly. But a better approach is to look at gamma of n plus 1. Well, here's our definition of gamma of n. If we want to find gamma of n plus 1, we just replace these n's with n plus 1. Now, if we replace this n with n plus 1, we get n plus 1 minus 1, which is just n. So gamma of n plus 1 is the integral from 0 to infinity of x to the n times e to the minus x dx. Now, how do we evaluate this integral? Well, we're going to use integration by parts. We will let u be this x to the n, and dv will be e to the negative x dx. And remember, the integration by parts formula says the integral of u dv equals uv minus the integral of v du. And you can work out the details, but for example, if u is x to the n, du will be n times x to the n minus 1 dx. And if this is what dv is, we can figure out what v is going to be. And it's actually a pretty straightforward computation. You end up getting this as your result. Now this first term out here, we have to evaluate from 0 to infinity. And at infinity, if you just plug in infinity, you get infinity over infinity. So you basically just have to use L'Hopital's rule, or just recognize that e to the x grows much faster than x to the n. So you end up getting 0 when you evaluate it at infinity. So you get 0 minus 0 plus n times, well, this integral is really just gamma of n. In fact, it's really just the definition of gamma of n. So notice that gamma of n plus 1 just ends up being n times gamma of n. And this is going to be extremely important for us. So I've written it right here. Gamma of n plus 1 is n times gamma of n. Now we're going to use these two pieces of information, that gamma of n plus 1 is n times gamma of n, and that gamma of 1 is 1, to find other values of gamma. So for example, what if we let n be 4 in this formula? What would the formula say? Well, it would say that gamma of 5 is 4 times gamma of 4. Right? So gamma of 5 is 4 times gamma of 4. Now what is gamma of 4? Well, if we let n be 3 in this formula, the formula would say gamma of 4 is 3 times gamma of 3. Right? So gamma of 4 is 3 times gamma of 3. And then gamma of 3 will be 2 times gamma of 2. And gamma of 2 is 1 times gamma of 1. And gamma of 1 is just 1. So notice gamma of 5 is 4 times 3 times 2 times 1. Of course, this is also just times 1, which is really 4 factorial. So notice gamma of 5 is 4 factorial. And you could do this for any positive integer. For example, gamma of 9 would be 8 factorial. And I've written this down. For any integer n greater than or equal to 1, gamma of n is n minus 1 factorial. So gamma of 5 was 4 factorial. And another way of writing this is that 4 factorial is gamma of 5. Well, the nice thing about this is this now allows us to define x factorial. In fact, we can define x factorial to be gamma of x plus 1. And this allows us to define factorial beyond just the integers. So x could be, for example, a decimal. So if x is, say, 5.3, how would we define 5.3 factorial? Well, it's defined to be gamma of 6.3. Which is defined to be this integral. Now, to actually figure out this integral, you would need to use some numerical approximation techniques or a computer to get that this integral is approximately 201.81. But that's how 5.3 factorial is defined. All right, now what about negative numbers? Well, remember that we defined gamma of n by way of this integral, but we assumed that n was a positive number. Now, why did we assume that n was positive? Well, it turns out that this integral diverges if n is less than or equal to 0. Now, this is an improper integral, of course, because of the right endpoint here. We're integrating out to infinity. But when n is less than 1, this becomes improper also at the left endpoint, at 0. And when n is less than 0, you get essentially an infinite area under the curve because of what is happening at 0, because of that vertical asymptote. In fact, let's use Desmos to kind of get a visual demonstration of that. So here's the function when n is 5. Now notice, as n gets smaller, what happens? Well, when n is 1, we get right here. This is what the function looks like. It's essentially just e to the negative x. If n is less than 1, though, we get a vertical asymptote. Now, when n is still bigger than 0, so n is 0.6 here, this vertical asymptote is still integrable. We still get a finite area there. But when n is 0 or less than 0, we're getting an infinite area here. We get an asymptote that's not integrable. So our integral diverges. So what this means is that if we're going to define gamma for negative numbers, we can't use this integral definition. But it turns out that we can still define gamma for negative numbers. So how do we do that? Now recall that gamma of n plus 1 is n times gamma of n. And by the way, to use this formula, you're not just assuming that n is an integer. This would also work, for example, if n is 7.3. So gamma of 8.3 would be 7.3 times gamma of 7.3. right? When we derived this formula, we made no assumption that n was an integer. So we could rewrite this formula as gamma of n is gamma of n plus 1 over n. And this formula is going to allow us to extend gamma to the negative numbers. Now let's assume, first of all, that we have a negative number that's between -1 and 0. So let's say like negative 0.2. Well, if we let n be negative 0.2 in this formula, what would it say? Well, it'd say gamma of negative 0.2 is equal to gamma of 0.8 over negative 0.2. But 0.8 is a positive number, so gamma is defined for it. And it turns out gamma of 0.8 is about 1.1642. And so we can define gamma of negative 0.2 to be gamma of 0.8 over negative 0.2, and we get an answer. And notice it's negative 5.821. Now, the reason that worked was because we had a number between -1 and 0, so that when we added 1, it became positive. So we'd have a little bit of a different issue, though, if we had tried to figure out gamma of negative 6.4, because then we'd have to figure it out in terms of gamma of negative 5.4. Okay, but we haven't defined gamma of negative 5.4 yet. So how would we do that? Well, what we just did extended the definition of gamma to the numbers between -1 and 0. Well, we can now extend the definition of gamma to the numbers between -2 and -1 by working our way backwards again. So for example, if we wanted to figure out gamma of negative 1.2, well, then based on this formula up here, it's going to be gamma of negative 0.2, divided by negative 1.2, and we already just found gamma of negative 0.2. And so we end up coming up with an answer. And then if we wanted to extend it back further again, we could figure out gamma of negative 2.2 based on gamma of negative 1.2. Then we could find gamma of negative 3.2 based on gamma of negative 2.2, and so on. And we keep working our way backwards. So this allows us to define gamma further and further to the left. Now, we do have an issue, though, with negative integers. Actually, with 0 and with negative integers. So for example, what if we tried to figure out gamma of 0 based on this formula? Well, it would say gamma of 0 is gamma of 1 divided by 0, and we're dividing by 0, so that's undefined. And we'd have the same issue with gamma of negative 1 now. If we plugged in negative 1, gamma of negative 1 would be gamma of 0 divided by negative 1, but gamma of 0 was undefined. So the fact that gamma of 0 is undefined means that gamma of negative 1 will be undefined, and the fact that gamma of negative 1 is undefined means that gamma of negative 2 will be undefined. So for 0 and for the negative integers, gamma will not be defined. But for every other real number, so every positive real number and every negative real number other than the negative integers and other than 0, gamma will be defined. In fact, this is what the graph of gamma looks like. Now notice that gamma of 1 is 1. It's really 0 factorial, which is 1. Gamma of 2 is also 1, which is 1 factorial. Gamma of 3 is 2. Okay, gamma of 3 is 2 factorial, which is 2. Gamma of 4 would be 6. It's 3 factorial. But notice as we get closer and closer to 0, we actually get this vertical asymptote. Now it's going to grow very, very quickly over here. Gamma of 5 is going to be 4 factorial, which is 24. But notice it's also defined for these negative values, but we end up having these vertical asymptotes that happen at 0 and at the negative integers. So this is what the graph of the gamma function looks like. In fact, we can graph gamma in Desmos. Now we have to kind of do it indirectly. What we do is graph x factorial, and this interprets this in terms of gamma. But remember, gamma of x is not x factorial. Gamma of x is really x minus 1 factorial. So if we want to see the gamma function, right, x minus 1 factorial. And this is what the graph of gamma looks like. So notice, for example, that the point 4, 6 is on the graph, because gamma of 4 is really 3 factorial, which is 6. Now remember at the beginning of the video, I mentioned that 1/2 factorial is the square root of pi over 2. Well, 1/2 factorial is really gamma of 3 halves. And it turns out that gamma of 3 halves is the square root of pi over 2. In fact, we have nice formulas for gamma of 1/2, gamma of 3 halves, 5 halves, 7 halves. These involve pi. So why is pi getting involved? Well, we'll see in a minute here. And also, we're going to define gamma for complex numbers. Okay, so for example, we could say, what is gamma of I? In fact, gamma will be defined for all complex numbers other than 0 and other than the negative real integers. We will also show a connection. It's really a mind-blowing connection between the gamma function and the sine function. And it's truly amazing. And finally, we'll show how the gamma function is related to the famous Euler-Mascheroni constant, as well as the Riemann zeta function, the zeta function that's famous in connection with the Riemann hypothesis. So there's really some beautiful math that we have still yet to see. So we'll first figure out gamma of 1/2. Now here's our definition of gamma, and we're going to plug in 1/2 for n. So notice we get x to the negative 1/2 power here. Now how do we evaluate this integral? Well, it turns out we can do it with a simple u substitution. In fact, not even integration by parts, just a u substitution. But it's not obvious what the u should be. In fact, the u is going to be x to the positive 1/2 power. And then du will be 1/2 x to the negative 1/2 power dx. So notice that this x to the negative 1/2 power dx, that's equal to 2 du. Multiply both sides here by 2. So what we end up getting is that this integral is equal to the integral from, well, when x is 0, u is 0, and when x is infinity, u is infinity. So it'll still be the integral from 0 to infinity. This x to the negative 1/2 dx, that becomes the 2 du. So we'll put a du here, we'll put the 2 here. Now what about e to the negative x? Well, what is x? Well, if u is x to the 1/2 power, u squared is equal to x. So notice we get e to the negative x, but that's e to the negative u squared. And of course now we can bring the 2 out in front of the integral. And what we end up with is gamma of 1/2 is equal to 2 times the integral from 0 to infinity of e to the negative u squared du. Now how do we evaluate this integral? Well, this is a very famous integral called the Gaussian integral. And if you've never seen how to evaluate it before, I will show you right now. Now the Gaussian integral is really the integral from negative infinity to infinity of e to the negative x squared dx. And that's really twice or double the integral that we're looking for, which was the integral from 0 to infinity. And the reason is because of the symmetry of e to the negative x squared around the y-axis. It's an even function. And notice, of course, they're also using x's instead of u's. But the graph of e to the negative x squared is this bell curve type shape. And the question is, what is the total area under this curve from negative infinity to infinity? Now it's going to turn out that the total area under the curve is the square root of pi. So let's show why that's the case. Now if you were just asked to evaluate this integral cold, how would you do this? Well, you'd probably think, okay, I need to find an antiderivative of this function. But the problem is there's no nice closed form for the antiderivative of e to the negative x squared. Now if we had, say, an x like out here, that would be great because then we could do a u substitution. We could do u equals negative x squared and the du would be negative 2x dx, and we have that x dx part that we need. But we don't have this x out here. So that kind of u substitution won't work. So how do we evaluate this? Well, we're going to have to get very clever. What we're going to do is to evaluate a totally different integral, a double integral. So this double integral of e to the negative x squared plus y squared, where we're integrating from negative infinity to infinity for both x and y. And somehow this double integral is going to help us find the value of that original integral. Now geometrically, what's happening here? Well, the graph of this function f of xy, is a surface. And it's really like a bell type surface. So not a bell curve, but a bell surface. So this integral is asking us to find the volume underneath this surface that's above the xy plane. So what we're going to do is to calculate this integral in two different ways. And when we do that, the value of our original integral that we're trying to find is going to pop out. Now, the first method we're going to use is an iterated integral. So we're going to rewrite our original integrand, e to the negative x squared plus y squared, as a product of a function of x times a function of y, e to the negative x squared times e to the negative y squared. And the fact that we can write it as a product in this way means that essentially we can split apart the integral into a product of two integrals. So for example, this e to the negative y squared, that can come outside of the inside integral that only involves x's, and you can split it apart like this. And notice that the two integrals that you get are really the same integral. You're just using a different variable, a different dummy variable. So this ends up just being this Gaussian integral that we're looking for squared. So one way of calculating this integral, we get this integral squared. Now, a second way to calculate this integral is to use polar coordinates. So we're going to change our x's and y's to r's and thetas. When we do this, x squared plus y squared becomes r squared, and the dx dy turns into r dr d theta. And this r here is very important. Now we're also integrating over the entire plane, and when we do that, the r goes from 0 to infinity, and the theta goes from 0 to 2 pi. Now this integral is much easier to do than the original integral e to the negative x squared because we have this r here. So we can do a u substitution. We can, for example, let u be r squared, and then du will be 2r dr. And when we do this u substitution, what we end up getting is this. It's actually a real simple substitution to do. I'll let you work out the details, but this is what you end up getting. And this is a very simple integral to do, and it ends up just giving you pi. So one way of calculating this integral gives you pi as a result. The other way of calculating the integral gives you this integral squared. So this integral squared should equal pi. All right, so summarizing here, one way of calculating the integral, we get this. Another way of calculating the integral, we get this. So these two things should be equal. So what that tells us is that this integral, without the squared, equals the square root of pi. Okay, now if we want to just integrate from 0 to infinity, we get the square root of pi over 2. So notice now we finally found the value of gamma of 1/2. Gamma of 1/2 was equal to 2 times this integral. So this is 2 times the square root of pi over 2, which simplifies to the square root of pi. So gamma of 1/2 is the square root of pi. And now that we have gamma of 1/2, we can use this formula to find gamma of 3/2 and gamma of 5/2 and gamma of 7/2 and so on. So for example, if n is 1/2 in this formula, this would say gamma of 3/2 equals 1/2 times gamma of 1/2. So gamma of 3/2 is 1/2 times gamma of 1/2, but gamma of 1/2 we just found was the square root of pi. So gamma of 3/2 is 1/2 the square root of pi. Gamma of 5/2 will be 3/2 times gamma of 3/2, right? If we let n be 3/2 in this formula, we get 3/2 times gamma of 3/2, but we just found that gamma of 3/2 was 1/2 the square root of pi. So gamma of 5/2 is 3/4 times the square root of pi. In fact, we see here gamma of 1/2, gamma of 3/2, gamma of 5/2, gamma of 7/2, and gamma of 9/2. We can find all these values based on that original value, gamma of 1/2, in combination with the fact that gamma of n plus 1 is n times gamma of n. Finally, what about complex numbers? Well, if the real part of a complex number z is greater than 0, we define gamma of z essentially the same way we did before, only we're using z here instead of n. So gamma of z is also defined by way of this integral. Now you have to know what it means to take a complex exponent, but it's really defined the same way. Now just like before, that only converges though if the real part of z is greater than 0. To define gamma of z for all complex numbers other than 0 and the negative integers, we have to do basically what we did before. Use this formula, gamma of z plus 1 is z times gamma of z, and kind of work our way backwards, work our way to the left through the complex plane. Now, a couple things about this complex function gamma. It's a holomorphic function, or in other words, it's an analytic function with poles at 0 and at the negative integers. Now, what does it mean to say that gamma is analytic in kind of plain terms? Well, it means that gamma isn't just a continuous extension of the factorial function to the complex numbers, but it's incredibly smooth. In fact, it's so smooth, almost beyond smooth in a certain sense, that if you know how it behaves in just a tiny little patch of the complex plane, then that's enough to determine how it behaves everywhere else, even very far away. And that's a deep and really beautiful property of analytic functions that you'll learn about if you study complex analysis. Now, it turns out that gamma doesn't have any zeros, so 1 over gamma is what's called an entire function. It's holomorphic on the whole plane, on the entire complex plane. Now, this next formula is truly incredible. It says gamma of z times gamma of 1 minus z is pi over sine of pi z. So gamma is intimately related with the sine function. In fact, we can think of this just in terms of x, so not a complex number z, but a real variable x. In fact, I've just rewritten it right here. Gamma of x times gamma of 1 minus x is pi over sine of pi x. Now, one way that you might be able to see some kind of connection between the left side and the right side is that both sides are going to have poles or asymptotes at the same values. So notice that at all integer values, sine of pi x is going to be 0. So we're going to get a vertical asymptote here at all the integers x. But remember that gamma has poles or vertical asymptotes at 0 and at the negative integers. And so gamma of 1 minus x, if you think about it, is going to have poles at the positive integers. So when you multiply these two together, you get poles at exactly the integers. So the same thing on both sides. But this equation is true for all the values of x that aren't integers. In fact, think about what happens when you plug in, say, 1/2 for x. We get gamma of a half times gamma of a half equals pi over sine of pi over 2. And if you work out the details, this is just another way of showing that gamma of 1/2 is the square root of pi. And notice here, we didn't need to resort to using the Gaussian integral or anything. The fact that gamma of 1/2 is the square root of pi just pops right out of this formula immediately. So it's a very quick result if you know this formula. Now think about what this says in terms of factorials. Now remember, gamma of x is really x minus 1 factorial. And gamma of 1 minus x is going to be 1 minus x minus 1 factorial, but 1 minus x minus 1 is really just minus x. So this formula says x minus 1 factorial times negative x factorial is equal to pi over sine of pi x. Now, of course, both sides are undefined when x is an integer, but even when x is not an integer, these are equal. In fact, in Desmos here, we can graph f of x equals x minus 1 factorial times negative x factorial, and this is the graph that we get. Well, now let's graph g of x equals pi over sine of pi x. And notice we get the same graph. In fact, notice both graphs have these vertical asymptotes that happen at the integers. So the factorial function and the sine function are intimately related like this, which seems totally surprising and unexpected as far as I'm concerned. So this is a beautiful little formula here, and it's true really for all complex numbers z. So you could even plug in, for example, z equals I into this formula. Now, one other thing we can say about the gamma function, and this is going to be related to the Euler-Mascheroni constant and the Riemann zeta function, is that if we look at the Laurent expansion of gamma about z equals 0. Now, the Laurent expansion is basically like a Taylor series expansion, only we allow for negative powers. So instead of just a constant plus a constant times z plus a constant times z squared, it's constant times z cubed and so on, we allow negative powers of z, so z to the negative 1. And the Laurent expansion is going to converge in the whole unit disk other than the origin, so really the punctured unit disk. But the Laurent expansion looks like this. It's 1 over z minus, this is the Euler-Mascheroni constant. And then here, as our coefficient of z, we have zeta of 2, which is really pi squared over 6. Okay, and we also have the Euler-Mascheroni constant appearing multiple times, and these zeta values appearing multiple times in the Laurent expansion of gamma about 0. So this is so amazing that the Euler-Mascheroni constant and the Riemann zeta function get involved with gamma. And there's so much more you could say about gamma. You could really go down so many rabbit trails. For example, you have infinite product expansions of gamma. So this means the infinite product. So instead of an infinite sum or infinite series, we have an infinite product expansion for sine. So this one up here is due to Euler. This one down here is due to Weierstrass. And notice this one down here involves E. And in fact, again, we have that Euler-Mascheroni constant right there in this product expansion for gamma. And in case you haven't seen it before, here's what the Euler-Mascheroni constant is. It's a famous constant. And the very last thing I want to say is that the gamma function also gets involved in formulas for the volume of a ball in n-dimensional space. So the volume of a ball of radius r in n-dimensional space is given by this formula. And notice we see the gamma of n over 2. And by the way, we know what gamma of n over 2 is exactly for every positive integer n, right? Because if n is even, we just get a nice, it's really just going to be like a factorial. If n is odd, we're going to get something that involves the square root of pi. But for example, the volume of a ball in three-dimensional space, if you work it out, you get 4/3 pi r cubed, which is actually the volume of a ball in three-dimensional space. If you looked at the volume of a ball in two-dimensional space, it really just gives you the area, and you end up getting pi r squared popping out of this formula. But you can ask, what's the volume of a ball in four-dimensional space or five-dimensional space? And you use this formula here that, notice, it involves gamma of n over 2. So there's so many things we could say about gamma. Well, I hope you've enjoyed this video on the gamma function. I'll make a couple more videos related to this. So for example, I'm thinking about doing a video on I factorial. And when I do that, I'll put the link in the description. So please like and subscribe and have a great day.